Hello, welcome back. In this lecture, we will continue our discussion on branch and bound algorithms using the second example problem, job assignment. After this lecture, you will have a more clear understanding of the branch and bound algorithm. A little recap. Branch and bound is often used to solve difficult optimization problems when we cannot find any efficient algorithms using divide and conquer, greedy, or dynamic programming. It appears that brute force is the last resort, but we are trying not to enumerate all possible full solutions. So we construct partial solutions one at a time and compute their lower and upper bounds for the best solution that can be achieved by extending a current partial solution. Based on the bounds, we eliminate as many of these partial solutions as possible. To have this idea work its best, we want to come up with bounds as close as possible. How do we compute these bounds? For the lower bound, remind ourselves that this is the bound for the best solution that can be achieved by extending a partial solution. Oftentimes, there are two parts that contribute to the lower bound. The cost so far, this is the cost already incurred by reaching to the current partial solution, and the guaranteed future cost. No matter which complete solution it is, this is the minimum cost of each decision yet to be made. So the lower bound is the sum of these two parts. What about the upper bound? It is from two parts as well. The cost so far is the actual cost already incurred getting to a partial solution this far, so it is also part of the upper bound. The second part is the feasible future cost. This is the summed cost incurred by the decisions that make during the extension process. The upper bound is the sum of these two. We can think of UP minus LP as the ambiguity of P. If they are far apart, we have very little knowledge about the best solution that extends the partial solution P. On the other hand, if they are close together, we have a very good estimate of the cost of the best solution that extends P. Also, the closer together we can bring UP and LP, the less likely that different partial solutions will have overlapping bounds. And if the bounds for two different partial solutions do not overlap, then we can throw one of them immediately. For instance, if we have one partial solution P1 that's bounded by 7, 15, and another partial solution P2 that's bounded by 12 and 20. We have to keep both of them because they overlap. There might be a best solution extending P2 that's better than the best solution extending P1. But if P1 is bounded by 7, 10, and P2 is bounded by 12, 20, then we can throw away P2 right away. We see that the best solution that extends P2 cannot be better than the best solution that extends P1. So we do not need to extend P2 at all. In fact, we can use P1 to update the global upper bound, and for any partial solutions with a lower bound greater than 10 can be thrown away immediately. Throwing away partial solutions is what branch and bound is all about. Typically, the number of partial solutions and potential full solutions is exponentially large. We want to keep the number of partial and full solutions that we actually deal with as small as possible. We do this by using our calculated bounds to eliminate partial solutions that cannot lead to an optimal solution. In this example of trail finding problem, a lot of information was given to us by the park. We treat this as sort of an oracle. In many real scenarios, we may not have such an oracle. That's what the admissible heuristic is for A-star algorithm. A well-guessed heuristic provides good upper bounds and can effectively eliminate a substantially large number of alternative partial solutions. For those of you not in the AI class and haven't heard about A star, it is okay. We will see how we can use greedy as a heuristic to help us find these upper bounds. Suppose we have n persons and n tasks. Each person is to be assigned to one of the tasks. Because people have different skill sets, the time required to complete the tasks can be different for each person. Our goal is to assign the tasks in such a way that the total time required is minimized. For instance, suppose we have 5 persons, P1, P2, P3, P4, and P5, and 5 tasks, T1 to T5. We can represent the time requirements with a matrix. This problem is relatively simple and does have a polynomial time algorithm. We use branch and bound to solve this problem and demonstrate the clever way we can apply to other problems that do not have polynomial time algorithms. Refer to the template of branch and bound. We first format the solution to this problem as a sequence of decisions. Of course, we could turn this around and make our ith decision to assign a person to the ith task. Next question, what is the initial global upper bound? Again, note that this is not the upper bound of all possible solutions, but the upper bound of the optimal solution. So we can simply generate one feasible solution and use its total cost as the initial global upper bound. The optimal solution's cost cannot be greater than that. One quick way to do this is to assign T1 to P1, T2 to P2, and so on. The total cost will be 73. And we can use it as our initial global upper bound. Remember that branch and bound works the most efficiently when the bounds are as close as possible. We can apply a simple greedy heuristic. We give P1 the task that they can do the fastest, that'll be T3, and then we assign T1 to P2 because that's the task they can do the fastest. We cannot assign T3 to P2 because T3 has already been assigned to P1. Then for P3, we have options T2, T4, and T5. We choose T2 because it has the smallest cost. For P4, we'll assign T4 that has the smallest cost. For P5, we assign T5 because it's the only one that's left. This is one feasible solution using the greedy heuristic. The result is 47. It is much better than 73, and we can use it as our initial global upper bound. Such a greedy heuristic takes a linear time to get the initial upper bound. Other smarter heuristics may come up with an even lower global upper bound, but cost more computation. This may be worth it if it results in a significant speedup of the algorithm. Now this algorithm proceeds as explained before. We look at all possible first decisions. We use a vector of length 5 like this to represent a partial solution. There are only 5 options for the first decision. Now we compute the bounds for each of the 5 partial solutions. Recall that the lower bound is comprised of the cost so far plus the guaranteed future cost. Again, we use the square brackets to represent the lower and upper bounds. For the first partial solution, it is easy to see that cost so far is 10 because we have already assigned T1 to P1. It will cost 10 hours. With T1 assigned to P1, P2 will cost at least 3 hours. P3 will cost at least 5 hours. P4 will cost at least 2 hours, and P5 will cost at least 2 hours. Even though all these cannot be in one solution, but they provide a solid lower bound. There's no optimal solution that can have a total cost lower than this. So the lower bound of this first partial solution will be 10 plus 3 plus 5 plus 2 plus 2. So that'll give us 22. For the upper bound, we need to figure out the feasible future cost, FFC. So now we need to come up with a feasible solution by extending the first partial solution. We can apply the same greedy heuristic. With the T1 assigned to P1, then we assign T3 to P2, and then we assign T2 to P3, and then we assign T4 to P4, and then we're left with T5 assigned to P5. This is a feasible solution by our greedy heuristic. Adding all these up will give us an upper bound of 49. Please pause the video and compute the bounds for the rest of the 4 partial solutions in the same way. Now we have the rest of our partial solutions computed. See, this partial solution's upper bound reduces the global upper bound to 46, and this partial solution's upper bound further lowers the global upper bound to 28. With the new global upper bound, we can immediately throw away the second partial solution. According to the algorithm, we choose the most promising one to extend further. That happens to be the last one. Since T5 is assigned to P1, the second decision will have 4 options, assigning T1, T2, T3, or T4 to P2. These 4 are the extended solution of this partial solution. We can reduce the matrix to this as well. Don't have to look at the first row and the last column. Now let's compute their bounds. For the first partial solution, the cost so far will be assigning T5 to P1 and T2 to P2. So that'll give us 9 plus 7. And then the GFC will include the minimum hours for P3, P4, and P5. So we have the lower bound plus 5 plus 2 plus 2. And then the upper bound would be the cost so far, 9 plus 7. And then we can use the greedy heuristic. After we have assigned T1 to P2, now we assign T2 to P3, and then we are left with T4 assigned to P4, and then T3 assigned to P5. So this feasible future cost would be plus 5, 6, and 2. This will give us a bound of 25 and 29. Please pause the video and see if you can come up with the upper and lower bounds for the rest of the 3 partial solutions. See, the last partial solution further reduced the global upper bound to 27, and this would allow us to immediately throw away these 2 partial solutions and also this partial solution. Now we are left with 1, 2, 3, and 4 partial solutions for future investigation. Among these 4 live partial solutions, again, we choose the one with the smallest lower bound. That will be this one. With assigning T1 to the first person, we have 4 options on the second decision. We can assign T2, T3, T4, or T5 to P2. These partial solutions are here. The table can be reduced like this. Now let's compute their bounds using the same idea. For the first of partial solutions here, we have cost so far. That's assigning T1 to P1, 10, plus assigning T2 to P2, 18. And then we have the FFC, that'll be 10 plus 6 plus 2. 10 plus 6 plus 2. And for the upper bound, we have the cost so far, 10 plus 18. And then we use the greedy heuristic. Once we have assigned T1 to P1, T2 to P2, we can just ignore these 2 columns and these 2 rows as well. And then we assign T5 to P3, T4 to P4, and T3 to P5. So this minimum solution is also a feasible solution. So the upper bound will be 10 plus 6 plus 2. That'll give us 46 and 46. We can actually eliminate this solution right away because it has a lower bound 46 that's greater than the global upper bound. Please pause the video and see if you can compute the lower and upper bounds for the rest of 3 partial solutions. Now we are left with 3 live partial solutions. The most promising one is this. We can continue the process and compute. We have computed about 20 partial solutions so far and will likely need to compute 20 more. If we use brute force, the total possible complete solutions will be 5 factorial. That'll be 120. So we have significantly reduced the branches we need to look at. Let's look at this algorithm again. We maintain a set P of potential partial solutions. We compute their lower and upper bounds. We always choose a partial solution P with the current smallest lower bound. If P is not a complete solution, we extend it by one more decision, and we delete this P from set P, since it is now represented by its multiple extensions in set P now. Get all solutions Q that extend P by one more decision. Compute the lower and upper bounds for each Q. If a Q has a lower bound greater than the global upper bound, we can discard this Q right away. Else, we'll see if we have seen a new lower upper bound and update the global upper bound if needed. We add these solutions to P. Now the complexity of this algorithm. Computing the lower and upper bounds of each partial solution may take big O of n or big O of n squared time, depending on what heuristic we use. What about choosing a P that has the smallest lower bound in set P? Note that we often apply branch and bound to problems where the number of potential solutions is exponential, so the way we store these P's makes a big difference on how quickly we can find a smallest one and how quickly we can add a new one. So how to store the set P? One option is to store set P in a list. When we generate new partial solutions, we can just add them to the end, which takes constant time. But then finding a partial solution P with the smallest lower bound will take big O of 2 to the power of n time, since we may have up to 2 to the power of n possible solutions. Another idea is to store P in a mini heap. Finding P with the smallest lower bound will take constant time. It is the first node. Adding a new partial solution will take big O of log t time, where t is the time of items in the heap. T may grow to 2 to the power of n, but log 2 to the power of n is n. This is not factorial, but an exclamation point. Again, we may need to remove an item in the heap, and we may need to reconstruct the heap. That will take big O of 2 to the power of n time again. We could consider keeping those obsolete items in the heap if memory is not an issue. As you have seen here, using the right data structure can significantly speed up the algorithm. So in theory, the complexity of branch and bound is still in big O of 2 to the power of n. However, as you have seen here, a carefully designed heuristic for computing the bounds can significantly reduce the number of possible solutions we need to investigate. In practice, branch and bound provides much faster solutions to extremely difficult problems where no efficient and clever algorithms can be found. I hope by now the idea of branch and bound becomes clear to you. Please do implement the branch and bound algorithm we discussed in this lecture. It will be very helpful. This is all for this lecture and for this week. Next week, we will be looking at the applications of branch and bound to 2 NP-hard problems. See you next week.